Hello, everyone, and welcome to an introductory session to epidemiology and biostatistics. Okay, I'm aware that this topic or this subject is kind of a pain point for a lot of people. But let's try to make it simple and try to understand what we mean by the different terminology involved. I just wanted to give you how this term study designs came about. What do we mean by that? First of all, people need to understand anything in science. And when I say science, I mean biology, which includes medicine. I mean chemistry. I mean engineering. I mean technology. All these are considered scientific fields, and they all share the need for creating new knowledge and new information. And traditionally, there is something called the scientific method. I'm sure every one of you heard of it. And this scientific method is actually a series of steps that's used to confirm or refute certain observations or theories that people had over time. Okay? Remember, science, as we know it now, with its different disciplines, wasn't that well formed or known or with this vast amount of knowledge like 2 centuries ago or 2.5 centuries ago. All this huge amount of knowledge came about fairly recently. People were believing in things that are really not spiritual things, myth, and trying to explain what happens around them in nature. Certain observant people, scientists, pioneers in all these fields, came about and tried to make sense of what they observe around them in nature, and along the way came up with this scientific method. Okay, so the scientific method is actually this series of steps, starting by some observation that we can formulate into a question. And then we go about trying to answer the question in a way that can convince people that what we are talking about is legit and it's a fact or a law of nature. And then when you have to, in order to convince people, you have to design an experiment or a study, and you do it and you go and collect your data and do your research and come back and analyze the data that you collected. And then finally, the final step is about making sense of what you found, or these data, these numbers. What do they mean to me? And here we are talking about healthcare. So we need to make sense of it within the scope of healthcare. Okay? But this general idea or this scientific method is actually applicable to any scientific field. That's how they do their research, or this is how they collect information and confirm knowledge, confirm new knowledge or new discoveries through the scientific method. So in the middle, we have these study designs. These are the experiments. These are the observations. These are the data that we collect, and then we analyze and interpret and see if we can use it. The knowledge coming out of this, is it usable? Can we generalize it to the general public? Can we use it with our patients? This is how we do evidence-based medicine, epidemiology, and we use biostatistics. Biostatistics comes here. You design a study, you collect your data, and you analyze your data. This is biostatistics. Okay? This whole series of steps is the scientific method, and it's modified to suit the healthcare and medical fields. Usually, all these studies or all these epidemiological studies start by studying a big population, a large population, and then you try to make sense of it and apply it to improve what you do to one individual who is your patient usually. Okay, so you collect information from the population, you analyze it, you interpret it, you see if it can make sense to apply it to your patients. That's how things happen. And all of this starts with a question that can be changed into a hypothesis. And basically, the question starts by some observation. As you are working on your patient, you said, why did this patient develop this condition? Meaning, what you are asking is, what put this patient at risk for developing this condition? For example, why this patient developed diabetes? You are looking for certain risk factors that put people at risk of developing diabetes. This is a question. This is an observation. You are trying to understand what kind of people develop diabetes, what kind of exposures or risk factors cause diabetes. Then you go and formulate what's called the hypothesis. Hypothesis is just a fancy term for adjusting the question, improving the shape of the question. Okay? Formulating testable predictions. Could this exposure be related to the disease? Meaning you ask a specific risk factor. In the case of diabetes, we can ask, could obesity be related to the development of diabetes? I want you to focus on this. I said obesity, and obesity here is considered something called exposure, and diabetes is called outcome. I want you to be very familiar with these two terms, exposure and outcome. Okay? So the hypothesis basically is to make the question very specific, focusing or honing on one particular exposure. Okay? You can't just ask a general question like this. What causes diabetes? You have to really be very specific. Okay? Then you go and design a study to try to test your question. And if you are asking about diabetes, you try to test if being fat, your study should test that. Then you look for the appropriate design based on your circumstances or this type of question. Every study spits out a lot of data and a lot of information that you need to analyze through biostatistics. And after you are done with your analysis, you sit down and interpret this information that you collected through your study and see if you can come up with a conclusion that is useful to medicine or to healthcare. For example, one of the conclusions should be we need to reduce or work on weight loss or fighting obesity to minimize the risk of the population getting or my patient getting diabetes. If I have a patient in front of me and I have a study, a very nice study, well designed and well done, and this study concluded that diabetes is strongly related to obesity. Okay. Then in my counseling or when I'm counseling my patient, I can tell them if you lose weight, the chances of developing diabetes goes down because there is a study that said that or discovered that there is a strong relation between being obese and developing diabetes. In general, that's how all of our knowledge in medicine and healthcare came about, through this method. Okay, before going forward, people need to remember, as I said, the scientific method is used in so many or in all scientific fields or scientific branches. But when you are dealing with biological specimens like humans, or biology in general, biology is full of uncertainty. You can never have two biological specimens, even within the same species, that are identical. Humans lived on this earth for thousands of years, and since they inhabited this earth, no two individuals are identical. Never. Even identical twins are not identical. Each individual is unique and different from the other one, and they react and respond to different stimuli and different phenomena around them differently. They respond to medications differently by either the desired response or by having side effects. Okay, so this makes it very difficult to test and experiment in biological specimens, including humans, of course. Okay, the other thing is any biological phenomena never exists as a single event or one number. Usually, biological phenomena exist in a spectrum or a range, okay? We use what is called probability of an event rather than sure or 100% certain that this event will happen. This never happens in biology or medicine. So it's about probabilities, confidence interval, and p-values. All these talk about how certain are you your real value exists in this range, okay? But it's never one number. I want you just to understand this. I want you to remember in engineering, for example, let's say mechanical engineering. In mechanical engineering, you are creating units, mechanical units. These can be cars, can be tractors, can be boats, anything that's engineered mechanically. And usually you create thousands of units that are built from the same exact parts. Okay, so you expect these units to behave exactly the same. They have the same speed, they have the same capacity, they have the same weight, everything is the same. So when you have a new discovery in engineering that tells you that if you added this piece to the engine, the engine will be very efficient and it will behave in 1, 2, 3 way. This is certain and will happen in all your units. All the new cars that has that piece will behave the same. So it's very easy for them to apply the new knowledge to their discoveries or to their new cars or something like that. And this is applicable to all kinds of fields. Engineering, technology, like computers and otherwise, you expect them to behave the same. You never have that certainty in humans or any biological specimens. And that's why when we report results of tests, lab results or something, we never say the normal hemoglobin is 13 grams. We never say that. We say it lies between 12 and 14. We never say the TSH is between 3. The normal TSH is 3. This means anything else above or below 3 is abnormal. We never say that. We say TSH normal value ranges between, let's say, 1 and 5, for example. Okay? People need to remember that. And this means the correct, and this is how we express results in the study results. We never express it in I'm certain that this number is the correct answer. There is nothing like that. And that's why when you apply new knowledge in medicine, and of course the application is in health, in patient care, you apply knowledge to patient care. You never take it as an absolute. You have to take it with a grain of salt. You have to apply the circumstances of your patient. You have to apply your clinical judgment besides the new knowledge. All these 3 factors need to be in play when you are applying evidence-based medicine. It might work for this patient, but never works for the second one or the next one. Okay? So that's one fact people need to approach this type of knowledge with. The fact that you need to remember going forward is in medicine, in healthcare, what we are doing when we design any study or when we study anything is we are studying 2 arms. One arm is called the exposure The other arm is called outcome. We are studying the association or the link between these two things, exposure and outcome. Exposure could be risk factor, like obesity and diabetes, for example. Obesity, a risk factor. Cigarette smoking is a risk factor. Physical inactivity could be a risk factor, and so on. Intervention, like I gave a statin to somebody, a medication, for example. This is an intervention. It's considered a form of exposure. Okay, this intervention could be a surgical intervention or a medical intervention, like giving a medicine, or any characteristic. Somebody who is like obesity, for example, is a characteristic. Some hereditary problem, being Down syndrome or being something like that, it's a characteristic, and it's an exposure. The outcome is what will happen as a result of being exposed to that, or the outcome is the disease process, like cigarette smoking is exposure, outcome is lung cancer. Okay, all studies are looking into this association, link between exposure and outcome. Please remember that. It will make your life much, much easier. Any study, no matter what the design is looking into an association between exposure and outcome. Okay, the outcome could be a disease or a recovery, changing the natural progression of a disease. Instead of it kills you eventually, we prolong your life because we gave you something. That something is the exposure. The outcome is prolonging your life. Okay, and so on. Death could be an outcome. Okay, so the classic example, and I will keep using this example, is smoking and lung cancer. Smoking considers the exposure, lung cancer is the outcome. Okay, when we talk about associations, we have different ways of expressing the association depending on what study and what circumstances are around your experiment or study. So there are different forms of expressions to tell me about this association. First of all, it will tell me whether there is an association or not. And number two, it will tell me how strong the association is. That's when it comes to the analysis and the interpretation of the data. Okay, one more information or one more fact you need to know about studies. There is no perfect study. None. Biology is full of uncertainty, full of ambiguity, full of idiosyncrasies. All these are things that make it difficult. And on top of that, if you want to design a study that's dealing with biological specimens, specifically humans, because now with humans we have this psychological element as well. If you are studying animals, like giving cows some medication or something and checking the effect through lab tests or something, the impact of the psychological effect, like placebo or nocebo or whatever, is not there. Cows are not that sophisticated. But us humans, we are difficult. We are difficult to kind of control. We have all kinds of idiosyncrasies that can impact this research. But within the study themselves, there are problems. No matter how much we try to make it perfect, but there are problems that are inherent to these studies as well. One of them is biases. Okay? And the bias is actually a systematic error that leads to incorrect estimates of association. Remember, my goal out of all these studies is to measure the association between exposure and outcome. That's it. Any study, exposure, outcome. To measure this association and to have the best possible result, you need to avoid these errors, these kinds of errors. One of them is biases. And the biases happen in the study itself. These are systemic errors that are inside the study. Okay? And they kind of make the results somehow skewed. They push the results towards this side or that side, away from the truth. The truth is sitting here. These biases push the results away from the truth. Okay, that's why they are considered systemic errors. And they are usually either problems with collecting information or problems with the sample or the population. So information and population. Okay. One of the examples is recall bias. If you are having questionnaire and asking people about information about their lives, how many meals do you take per day? How many cigarettes do you have? Questions. And if they ask the information that are distant, last week, last month, last year, they might not remember correctly. So here, the way you collect information is biased by something called recall bias. They cannot remember. They will give you false or wrong information, or they invent things. And since your data are not clean, then you will not get good results. Okay? And so on. We'll talk about biases at some other point. Now, there is this confounding, and I would like you to clearly differentiate between bias and confounding. Bias, problem with the study, either in the way you collect information or the population sampling and the controls and the cases. So either the population or the participants in the study or the information collected, they are not good. They are distorted by these biases. And we have a lot of biases, a lot of types of biases. Confounding is a very specific problem. It's not a bias, but a problem by some other factor present in the environment that we are not looking at. A variable, third variable, associated with both exposure and outcome that distorts the true relationship between them. For example, if I'm checking a study or I'm designing a study to check the relationship between alcohol or heavy alcohol drinking and coronary artery disease or heart disease, let's say just heart disease. Okay, I'm trying to design a study to check or to find the relationship or the association between alcohol drinking and heart disease. Okay, if I neglected the other factor, which could be cigarette smoking. Cigarette smoking is known to be associated with increased risk for heart disease. There is an association already established between cigarette smoking and heart disease. People who drink alcohol, especially heavily, they smoke more than other people. Here, cigarette smoking is considered a confounder, a third variable that is present more in people who drink more, who are the drinking cohort, the cohort that I'm studying, and I need to be cognizant about that. I need to consider it because this is another risk factor that's present more in my study population and might affect my results. I might wrongly assume heavy drinking causes more heart disease, while it's not really the truth. The truth is heavy drinkers smoke more. That's why they appear to have more heart disease. And these are considered distortions. Thank you. Considered distortions, meaning what? They affect the quality of the results, and they affect the quality of this association between exposure and outcome. Either having biases within the study, which are systemic errors within the study, or a confounding variable that I didn't look at carefully, or some other random errors, okay? And this could be because of so many other things, other technical errors or statistical analysis can have some problems associated with it and so on. But what I wanted to make sure you understand is the difference between bias and confounding. When you are trying to critically appraise a study, you focus on this information. Did they pay attention to minimize bias and confounding, for example? This is one of the things that we look at when we are trying to appraise a study and see if it's a good study that we can use or it's a rubbish that we really just throw in the garbage. This is one of the information. Bias and how they dealt with it, and confounding or any other random errors present. Okay, we'll have a chance to discuss that further, but I want you to just understand the general idea. Okay, so the types of questions in healthcare that might result in triggering a study or an experiment or and so on, things like causation questions. Does the exposure cause the outcome? How strong the relationship between the exposure to the outcome? Okay, they're considered causation problem. Okay, and in that case, the RCTs, which are the randomized controlled trials, these are the gold standard. They are the highest ranking types of studies. The best information or evidence comes out of RCTs, randomized controlled trial. In medicine, we call it trial. In other disciplines, I don't think they call it trial, but here it's a clinical trial. Of course, clinical is a term that's used just for medicine, but it's a randomized controlled trial, and this is the best kind of evidence that comes out of it. If you want to clearly link a certain exposure to a certain outcome, this is the best design. For example, if you are testing a medication, and these are interventional types of studies, meaning you are giving patients something. So if you are looking into statin medications, statin medication is the exposure, and the outcome can be either reduce heart disease or reduce vascular disease, heart disease, or reduce cholesterol. These both outcomes are valid when it comes to statins. So the best way to get these kind of, statins cause improvement in cholesterol level. It's a causation association or causation question, and the best way to establish that relationship is through RCTs. Exposure comparison. Is this exposure more common in cases than controls? Okay, this is here the case control studies. We'll come to that. You start with a case, like cases of lung cancer. They call it case control because you have cases and you have matched controls who don't have the condition. Cases that are the ones who have the condition, and you go back in time looking for what type of exposure they were exposed to. For example, were they smokers? Were they exposed to smoking? So you start from the outcome and you go back in time looking for the exposure. This is a case control study. So exposure comparison, usually we use case control. Prevalence questions, this is usually cross-sectional. Cross-sectional studies are just a snapshot studies, meaning one point in time, you want to know the percentage of people having diabetes in this village. I have a village with 1,000 people, 1,000 residents. So I come and ask them, do you have diabetes? Yes or no? Yes, I put them under yes and no under no. And then eventually you come and calculate the prevalence. The prevalence means the percentage of people who have the disease at that time. It doesn't tell me what will happen tomorrow or after 1 year or what was happening last year. It will just tell me at this point in time what is happening. And that's exactly what we mean by prevalence. Diagnostic accuracy, this is about diagnostic tests. And they usually compare a gold standard test, the best test available for that condition, with your new test. Prognosis questions. So all sorts of questions, and you need to match them to the correct study design. Okay, now let's talk about how to classify studies or how to classify study designs. You can classify them in multiple ways. One of them is the famous classification of observational and experimental. When I say an observational study, I mean I'm not going to impose any kind of intervention on this study groups or people under study. I'm just going to observe them, monitor them, and follow them over time. Either look at them retrospectively. Retrospective means back in time. If you go back in time, it's retrospective. And usually this is case controls. And a case control study is, case means people who has the condition, the outcome, people who has the outcome. Let's say lung cancer. So case control, the cases are the people with the condition. Control is the other group. And usually studies are done along two branches of people, the study group and the control group. The control group are groups that are not, either they are not subjected to the intervention or they don't have the condition. Why? For purposes of comparison, because when you are coming to interpreting the information out of this study, you have to compare it with neutral people, people who don't have the disease, and compare the two results. Those who have the disease, and when I followed them back in time, I found out that 30% of them actually smoked cigarettes, or 50%, or whatever. Okay? The controls who don't have the disease, when we looked at their behavior in the past in terms of exposure to cigarette smoking, it's only 5%. Then most likely when you start to analyze the studies, you do a 2x2 table and come up with all kinds of results. In cases of case control, we use a measure of association called odds ratio. We'll come to that. But odds ratio is the measure of association that we use with case control studies. Okay? Another observation study. So I want you to realize we didn't do anything to these people. They were diagnosed with lung cancer. So I studied their past history in terms of cigarette smoking. Looked back retrospectively into whether they had the exposure or not. The exposure here is cigarette smoking. There is another observational study, which is called cohort study. Cohort study goes into the opposite direction. Cohort study is you start from now and you go to the future, forward, prospective. Prospective. This is retrospective. This is prospective. Okay? And both these studies, these observation studies, has some temporality to them, meaning you are looking at some timeline. Okay? Either in the past or in the future. The cohort study starts with the exposure, meaning if I'm going to use the same example as cigarette smoking, I'm going to follow people who smoke over time and see how much of them or how many of them will develop lung cancer. And this usually takes a long time, years and years, especially conditions like cancer and stuff, needs a long time to develop. So they usually take a long time to monitor these people and follow them up. The most famous and the most maybe impactful study, cohort study in the history of medicine is Framingham study. I think you heard of it, most of you. Anybody heard of the Framingham study? The Framingham study started in the early 60s. I think it's the late 50s, 1950s. Still running. So many years. So many years. It's still running. And most of the information we know about risk factors for heart disease and risk factors for other chronic medical problems were found and discovered out of this study. Okay? I'm not sure. I think it's the city, the town that the people who are being studied is named Framingham in Massachusetts or something, one of these states. They started by that the first generation of course, they aged out and most of them died. Then they recruited their children from the same place and continued. And I think now they are even recruiting their grandchildren. So they continued with the multiple generations of people along this period of time. Framingham study, go and read about it. Very important study, very impactful. And a lot of health information that now we use. All these risk factors, by the way, for heart disease were not known when these people were being studied. Okay? For example, smoking linked with heart disease through this study, one of the things that were discovered, these associations. Okay, so cohort studies go into the future. You follow people along some time and you start from the exposure and you look for the outcome. The outcome happens as you go. So it's a prospective. Case control, the opposite. You start from the case, the outcome, and you go back in time looking for the exposure. So it's retrospective. Here in the now is the cross-sectional study. Cross-sectional studies are also considered observation studies. Okay? And they happen just in a kind of a snapshot in time. You measure something now, like prevalence of a disease or prevalence of a habit or something like that. It doesn't give you any good association. You can't come up with an association as a result of cross-sectional studies. It doesn't give you time link. Temporality, no temporality. Experimental studies are studies where you actually do something to the participants, either surgical procedure or some form of intervention or medication. And all these medicines, new medicines that come up every day, they do these kinds of studies, experimental studies. And of course, the main people now, or the main entities that are doing these studies, are pharmaceutical companies, because each company wants to discover something that will bring them billions and billions of dollars. Okay? So they are doing these kinds of studies and coming up with new interventions and new devices, new surgeries, new procedures, whatever. Okay. So this is one way. And the experimental studies are called RCTs, okay? Randomized controlled trials. And these are the best type of, if you want to look for causation and a strong relationship between an exposure and outcome, the best way to do that is through an RCT studies. Descriptive studies means what? It's not exactly studies, but this is just reports, like case report. Somebody came across a very interesting case, unusual case, and he wrote an article about it and published it in one of the journals. This is called case report. One case. You can have a case series if you had similar cases coming to you with the same description and you kind of kept tab of that, a collection of similar cases. So it's descriptive. Okay? Even cross-sectional surveys or studies are considered descriptive studies. Ecological studies, these are about outbreaks of diseases, that health outcome. Okay, way of looking at studies, it could be retrospective, going back in time, or cross-sectional, just a snapshot in time now, or prospective, meaning going into the future, follow up into the future. This is another way that you can classify studies as well. Okay, what's the conclusion out of that? Medical research is mirroring the scientific method, which is used in so many or in all scientific disciplines. It's not just in medicine, but we have it modified a little bit to adapt to what we need. Healthcare and biology is different from other disciplines. Variability and uncertainty are fundamental. They are inherent to these disciplines, and we cannot really ignore that, and we cannot overcome that. But we have to modify what we do to extract information, knowing this uncertainty. Studies usually gives you associations between exposure and outcome. In medicine, that's what we are doing, exposure outcome. Bias and confounding are inevitable but manageable. We have a lot of tricks to try to manage biases and confounding to minimize their effect or impact on the results. Okay, research questions dictate the study design. Study designs fall under observational or experimental categories. So this is the introduction. Now, I want to ask you, I have another part talking about study designs. It's more detailed. It has the study designs more explained and the measures of association linked to each study design. So it can be longer than this. Are you ready, or do you want to discuss this and we do this some other day?
I think some other day for me.
Okay. Okay,
I
I think
agree.
that's reasonable. If anybody has a question or some point to explain or discussion, please feel free.
I guess, Dr. Sarah, your explanation is so clear. Usually, when we come to solve the question, where we find it really difficult and we sometimes mix up between,
I
the test
understand.
report and all that.
Yeah, I understand. But I wanted to make it as simple as possible so that when we go forward with more complex or more information, people have this baseline understanding. Okay? That's why I try to highlight these things.
Yes, it's really clear. Thank you so much.
Thank you. Okay, ask me questions. Is anybody using the chat? I can't see the chat. Riham, who? Who is Riham?
That's me. Hi. Hi, doctor.
Hi. I have a daughter whose name is Riham.
Oh, really?
My second daughter. That's why.
Yeah. Thank you,
Okay.
doctor.
Welcome. Hi.
Mm.
So this is the subject for next time. It's called Study Designs and Measures of Association. Now, here is what I'm going to recommend. This lesson or lecture or whatever you can name it, call it, I will edit it a little bit and put it in my channel. Okay? So you can find it and review it so that next time you come prepared and try to read whatever came into whatever we mentioned so that next time you might ask some questions for clarification or something. Okay? So let me try to increase the number of followers. Follow me in my YouTube channel so that you can find these lessons. I will try